So we use this formula if sigma is known, which again is not very realistic. But now we're going to talk about the more realistic formula when sigma is not known. But before I just give you the formula, let's look at the previous formula. If you look at this sigma divided by the square root of n, does it ring any bells based on what we've talked about before in the past?
Standard deviation for what sample standard deviation?
Yeah, close. So this is when we talked about the central limit theorem, and we said that if you have a distribution of sample means, then you're going to get a bell curve. But that bell curve will have a certain mean and standard deviation. Remember, we said that the standard deviation of this new bell curve ends up being the previous population standard deviation divided by the square root of n. And this is when we have a distribution of sample means. So sample means, I'll just write it out. We have a distribution of sample means. That means that you take repeated samples and you find the means of those. If you plot the distribution, then the distribution ends up being a bell curve with this new standard deviation. So this was the central limit theorem that we talked about. And this central limit theorem relied on knowing this population standard deviation here in order to get the new standard deviation of this bell curve. But again, we said that this population standard deviation was not really that feasible to know. So it turns out that if you plot the distribution of sample means when sigma is known, then you get this bell curve. But in the more realistic case, if you plot the distribution of sample means, and in the realistic case, when sigma is unknown, then it turns out that you get this new distribution. It's no longer a bell curve, but it looks similar to a bell curve. It turns out that the distribution looks like this. So it looks similar to a bell curve. The peak is a little bit sharper. This is something that we call a t-distribution. So to give you some context, this was invented by a mathematician in the late 1800s, like 1890 something. And he was actually employed by a beer production company. You might have heard of it. It was Guinness. So he worked for Guinness, and his job was to model the average beer production volumes that came out of a six-pack of beer. So basically, you have different six-packs of beers. In other words, different samples of size 6. So he had different six-packs of beers, and he wanted to model the average beer volume in each six-pack. So basically, he had a sample of size 6, and he wanted to find the average of that sample of 6. So he wanted to find the sample mean of the beer volume in those 6 bottles of beer in each six-pack. So he found that the traditional bell curve just didn't model that average beer volume in a six-pack very well. So he came up with his own distribution. And his own distribution ended up being this distribution here. And he found out that it modeled the average beer production volume in a six-pack very well. And he was really excited about this, and he wanted to publish his results and share this with the world. But unfortunately, this being the late 1800s, and even today, it turned out that this information was proprietary to the company. and they didn't let him publish the results. And so in the name of science, he did it anyway. But he still wanted to keep his job, so he used a fake name. So he used the name of student. So to this day, this is called a student distribution, even though this distribution has nothing to do with students or teachers or academics or anything like that. It's just the arbitrary fake name he called himself when he published this for the first time. So this is called a student distribution. And you would think that to abbreviate this, we might call this an S distribution, but S is already reserved for sample standard deviation. So now this is called the last letter in student, which is a T distribution. So the point of this is when you see a student distribution, you'll know it's a T distribution, but also the point of this is to show you that a lot of things that involve human activity are often sometimes arbitrary. So this is called a T distribution. Any questions? Okay, so the point is if you have a variable that involves the sample mean, and your sigma, which is the original population standard deviation, is not known, then you can model these sample means under that situation with this new distribution called a T distribution or student distribution. So it looks similar to a bell curve, but a little sharper in the peaks, so a little bit different from a bell curve. So it turns out that if you're to try to estimate the true population mean when sigma is unknown, i.e. the more realistic practical case, then now there's a different formula for the confidence interval, but it's actually kind of similar to the one that we just talked about. So it ends up being this. So you notice if you compare these two formulas, the structure is the same. The only difference is instead of using a z-score here, we use a t-score. And instead of using the population standard deviation, which we said that is not practical or realistic to know, we use the S, which is the sample standard deviation. It turns out the sample standard deviation is directly from the sample, so you'll always know that. Okay, so let's use the previous example that we just talked about. So if you gather a sample, and let's say that you have 50 people in the sample. The example before was that if you gave each of the 50 people an IQ test and you plugged in those 50 results to your calculator will give you the statistics for that sample, which is the sample mean and the sample standard deviation. So let's say that the sample mean is 102 and the sample standard deviation is 14. And let's say that in this case now, we no longer know sigma, like we did before. So let's say we don't know this anymore. Because it's not realistic to know that. So we're not going to use this formula. So let's go ahead and plug things in, and then we'll talk about this t-score, which is new. So x bar is 102, that's given in the sample, plus or minus this t-score we'll talk about, and then s is given as 14, and then divide by the square root of n, which is the square root of 50. And the only quantity left in this formula is this t-score, so let's talk about that. So the t-score, again, would look something kind of similar as before. Let's say this. And just like finding the z-score before, we used a table. Now, to find the t-score, we're gonna do the same thing, use a table, but a different table. So, let's first talk about how this table is laid out, and then we'll look at the table together. So when you look at the table, the first column you'll see in the t-score table this first column here will be something called degrees of freedom. And that will be abbreviated as D.F. And degrees of freedom is defined as n minus the number of variables. And it turns out that all the statistics we've done so far, if you notice, if you use your calculator, and your calculator asks you whether it's one variable statistics or two variable statistics, you've always been picking one variable statistics. So the reason for that is all these numbers that we're observing in the sample represent values of a single variable. So these 50 numbers represent values of one variable that in this case represent IQ scores. So the number of variables here is going to be 1. Later on in the semester, if we have time, then we might do two variable statistics. But I'll let you know when that time comes. But so far, we've been doing one variable statistics. So this is going to be n minus 1. So in the first column, we're going to look for the degrees of freedom, which is n minus 1. And so in this example, it'll be 50 minus 1, which is 49. So we're going to look for 49. But if 49 is not there, then we're going to pick the closest number to 49. And then we're going to scroll over. And then the first two rows in the column will be labeled this way. It'll be area in one tail in the first row, or area in two tails. So let's talk about what that means. So the confidence level will be given, let's say it's 95%. So in the picture, what that corresponds to is, it corresponds to this area that surrounds the mean will add up to the 95%. And that's going to leave out these two extreme areas that are either too high or too low. We call those extreme areas the tails of the distribution. So these two extreme areas, or the two tails, the shaded areas, add up to how much?
5%.
Yeah, they add up to what's left from this, from 100%. If you exclude the middle area of 95%, so they add up to 5%. So everything should add up to 100%. So the two tails together add up to 5%. So that means that each tail individually should be how much? Yeah, so half of 5%, which is 2.5%. So I'll write that down. 5% divided by 2, which is 2.5%. So if you look at the table here, we want to search for both tails should add up to 5%. So in the area in two tails row, we're going to look for 5%. But also, in the exact same column, you'll see area in one tail as being 2.5%. So in other words, you can use either row to look up the appropriate column to go to. So in the same column will be area in two tails of 5%, and also area in one tail is 2.5%. It's just saving you like having to multiply or divide by 2. But later, when we talk about hypothesis testing, there'll be a more substantive reason for the table to list both these together. But right now, you can use either row. Okay, so using either row, we get this particular column, and then that column, we would just intersect with the degrees of freedom, and it'll give you this t-score. So let's go ahead and use the table together. Go ahead and pull out the packet that I passed out in one of the classes. And if anybody needs one, let me know. Anybody else need one? Okay, so go ahead and flip to the t-score table. So this will be the page after the z-score table. And then go down to degrees of freedom. Look for the closest number to 49. So on the table, what is that going to be? Yeah, 50. So 49 doesn't appear exactly, so we're going to pick the closest one, which turns out to be 50. And then we're going to scroll over to the appropriate column, where if you look in the first row, it says area 1 tail. Look for 2.5%. And then go down to meet that degrees of freedom of 50. And you'll see that in that column where area 1 tail is 2.5%, it will be the same column where area 2 tails is 5%. So if you intersect that column with 50 degrees of freedom, what number do you get? What is it? 2.009. Okay. Anybody have any questions using this table? Yeah.
Might have missed it, but how exactly do we get to the 95 and 5% for the tails again?
Okay, so that's based on the confidence level that's given. So the given confidence level is this 95%. So visually, what that means is that the area around the mean, or this peak, is 95%. So that leaves out these two extreme areas that we call the tails.
All right.
Yeah. And the two tails then add up to the remaining 5%. And then each tail is half of the 5%, 14.5%. Any other questions? So this number that we see, 2.009, represents this t-score that we're going to use directly in this formula. So that's going to be the 2.009. So now that we have all the pieces in the formula, let's go ahead and plug this in. Now let's go ahead and calculate the quantity after the plus or minus first. Or let's calculate the margin of error.
So for this example specifically, it's going down to middle after the table?
Yeah, for this example specifically, you'll see that the 0.05 in two tails ends up being the column in the middle of the table.
And this is based on the confidence level.
Yeah, it's based on the given confidence level of 95%. So that means the remaining two tails have to add up to 5%, and each one tail is half of that, and it's going to be the same column.
But how would we identify 90%?
Okay, so we'll do that example in a moment.
Okay.
Yeah,
The error bar is 3.9.
3.98, great. So what does this tell us? It tells us that in the more realistic case, when we actually do not know sigma, which we used in the previous formula, sigma is the population standard deviation, we don't know that. So instead, we're going to use this modified formula that involves the t-score and doesn't require sigma, but uses S, the sample standard deviation, instead. So using this formula, we get this answer for the population mean, saying the population mean is somewhere in this interval, 95% of the time.
So how do you like find it on the table again? Cause didn't we subtract by one? Like, in the T?
Yeah, so this new table, this T-score table now, has a different convention now. So we start with degrees of freedom, or n-1, which would be 49 in this case, but 49 is not there exactly, so we pick the closest one. And then this row needs to be intersected with the correct column. And the way that we find that column is we use either the first row or the second row, it doesn't matter. So the first row says area 1 tail, and area 1 tail would be, each tail here is 2.5%, so that they add up to 5. So area 1 tail would be 2.5%. So then you would go down to that column and intersect it with the row of 50 degrees of freedom.
So-
Or you could use the other, the same column representing area 2 tails as 5%.
And if we got a number like 46, or no, not 46, but like 56, and then we subtract 1 and it's 55, would we choose between 50 or 60 in that case?
Okay, I'm not gonna do that to you.
Okay.
Yeah. So in that case where there's ambiguity, I'm not gonna do that to you. But in general, pick the one that's the closest.
Right.
I'm sorry, so we'll just, that's just our final T-score, we don't have to do the alpha divided by 2 and all that? For the 2 points?
Yeah, that's the final T-score. Because this is actually, you don't actually have to do this to use that table.
Okay.
But what this actually means is find the T-score with this much area to the right of it. So if you were to do all that, you would see that the confidence level is 95%, that means alpha is 5%. So alpha is 5%, alpha divided by 2 would be 2.5%. So you're looking for the T-score that has a right area of 2.5%. So right area of 2.5% would be right here. So it's the same picture that we drew, it's just that the convention of the table allows us to find it without having to calculate it.
Okay, yeah, just double checking, thank you.
Sure.
In the original formula, when we do have sigma over square root of 9, why can't we just plug in the sample standard deviation as the central limit theorem says? Isn't that the same formula to find the sample standard deviation in the central limit theorem?
Yeah, because the central limit theorem is saying that the distribution of sample means ends up being a bell curve with this new standard deviation, which requires a population standard deviation.
Okay,
So it ends up being a bell curve if you know what sigma is. But if you don't know what sigma is, then we have to use this new distribution, this T distribution.
so we can't just plug in the sample standard deviation into that entire equation. We have to find out.
Yeah, if you plug in the sample standard deviation, then this z-score would be, it would be different. So you would have to use a t-score if you use the sample standard deviation, and a z-score if you use the sigma. Because the z-score pertains to an underlying distribution that is a bell curve, and a t-score pertains to an underlying distribution that is this new t distribution. Okay, good question. Anybody else? All right. So if you're trying to find the population mean and sigma is unknown, then you use this formula, which involves this new t-score that we talked about. And we talked about how to use this t-score table in order to find that t-score. And then the result is this confidence interval that you got, which represents the interval where the true mean value actually lies within, and it lies inside this interval 95% of the time, which corresponds to the given confidence level of 95%. Okay, any questions? All right, so keep in mind that so far we've talked about finding the sample size that is needed in these two cases when you're estimating the proportion of success and you're estimating the population mean when sigma is known. We've talked about how to use a little bit of algebra to solve for the n here. But if we're using this new formula, it turns out that I'm not gonna ask you to solve for n here. And the reason for that is because when you try to look up the t-score in the chart, you need to know what n is in the first place to find the degrees of freedom in the table. So degrees of freedom is here, you need to know what n is to begin with. So I'm not gonna ask you to find the sample size that's needed in this case when this formula is involved, because it would be like circular, because you would have to use the t-score chart to find n to begin with, and you don't know what n is. So I'm not gonna ask you to find the sample size that's needed in this case. Okay, so in the time we have left, let's talk about the last measurement that we're concerned with estimating for the population using the sample.